to the point P where two curves are in the same equivalence class, that is, two curves represent the same vector, if and only if they're tangent to each other. That only pushes it back one step. What does it mean for two curves to be tangent to each other? And for that, we used the chart, we used the usual strategy of transferring everything to a chart, IMF C, which we use to define the manifold itself and define smoothness. And maybe there's another chart here. So this is B8, this is BC. We said that the question now is, when are two curves in the manifold through P, when are they tangent to each other? And we made the condition, the criterion for it to be so, that the two curves are tangent here, if and only if their images in the chart are tangent. So these perhaps two curves goes to finding this vector here that I just obscured with the orange chalk. And they're tangent, we define them as tangent here, if and only if they're tangent here. So what we didn't check is that this is entirely well defined, because suppose we take another chart, how do we know that the two curves, which seem to be tangent from the point of view of this chart, are they also tangent from the point of view of this other chart? If that were not so, then the definition would not be intrinsic. It wouldn't be even a well-defined concept, because you'd have to specify in which chart you're talking about tangency. Of course, we wouldn't be doing this if it wasn't consistent. So I'll come back in a moment and we'll prove this coherency or this consistency of the definition, that it's chart independent. But first, I want to finish the development by defining, we define vectors, but we haven't really defined a tangent space yet. That is, we have the elements of the vector space, but we haven't shown in what sense it is a vector space, meaning in what sense you can add vectors and subtract vectors and multiply vectors by scalars. So we need to define the sum of two vectors, and so we call the typical tangent vector. I was using the notation U. We want to define U1 plus U2, and also I put it in parentheses because it's sort of more trivial, but we also need to define lambda times U for some real number lambda. That's, if you're familiar with, I assume probably everyone has one place or another seen the definition of a vector space, and it's a space in which you can add the elements and multiply the elements by a scalar, and a few other technical and more trivial things like you should have a zero vector and so on. So how do we do it? Well, of course we're going to use the same idea. We're going to transfer the vectors from here to one of the chart codomains, one of these codomain spaces of the chart, that is space to which the chart maps everything. By the way we set things up, that is a vector space. And so there we know how to add vectors. And then we'll just transfer that definition back to the tangent space in the manifold. Okay, so how do we do that? Well, basically, what we need to do is associate with every point, with every vector at a point P and every chart C, a vector at the corresponding point. I'll take that corresponding point to be the origin. So I'll just assume, just for convenience, that C of P is equal to 0. That is the zero vector in the vector space P sub C. Assuming that, we need to transfer this tangent vector in the manifold to a vector in the vector space C. But we've already done that, really. So what are we saying? We have I should write the terminology. Also, these curves were called gamma. So the picture of spaces for that is we have a map gamma from the real numbers into the manifold. In other words, just a parameterized point in the manifold. And that by the chart map is going to peak C. So therefore we get a curve, of course we get a curve in the manifold as we just saw, as we saw last time. And of course I'm going to define the vector corresponding to this vector u as the tangent vector to that curve in the vector space, but we know what it means. So just to formalize that, I'll define a map C star, substar as it's called, at the point P, which will map the tangent space of P to, that is, it will map vectors at the point P into vectors in the vector space C. C. And how will we do it? Well, we'll just say that C sub u, C sub P of u, so applied to u, I'll use this dot to show that it's applied to u, is just equal to the obvious thing, or what I just said in words. It's the tangent to the image of the curve gamma. So if gamma is an element of the, if gamma is in the equivalence class of this vector, so this looks a little weird, gamma is an element of u, but in writing that I'm thinking that u is an equivalence class of curves. So this means gamma is one of the curves in that equivalence class. Then we define C star of P to u, this C star push forward sometimes it's called, that to be the derivative of the curve in V and lambda equals 0. So that's the definition. That's the definition of this. Yeah, but it's the obvious one. So it's saying the tangent vector to a curve here goes over to the tangent of the image curve, tangent vector of the image curve in the vector space C. Now, once we have this, then we can map vectors, we can map between vectors in the manifold itself and vectors in this chart space, V sub C. Or we can do that if we can check if map between vectors here and vectors here is a bijection, if it's one-to-one invertible. If that's true, then if we want to add two vectors here, two vectors here, we just push them forward here, add them, and then pull back the sum back to the tangent space. Okay. So just to make things, for this all to be consistent, we need to prove a little lemma, so I'm trying to be very careful and rigorous just here, just to show how you would do things if you wanted to be careful and rigorous. I won't always try to be this careful, but just to illustrate how one can, if necessary. And it's usually necessary only when you get confused by something. So this map is well defined, and it's a bijection. So here's the proof for illustration. So first of all, why is it well defined? Well, if you think about it, it's well defined just by definition. If you just think what it means for two curves gamma to be in the same equivalence class, it means precisely that their images in this vector space V have the same tangent. And we've defined C of u to be that tangent. So this is trivial. This is what it's not only trivial, it's what sometimes is called immediate. It's just a rewording of the definition of a vector. and given tangency of two curves. So that's trivial. Almost as trivial. I want to show that this map, so this is saying that C star is defined. Now I want to show that C star is injective. So what does that mean? That means that if I have two distinct vectors here, then they go over to two distinct vectors in V. If that weren't true, then we obviously lose information about the vectors. So that's also almost trivial. So to turn it around, so this says if these two vectors are different here, then their images in V are different. So to say it in the opposite way, if the images were the same here, then it must be the same vector. So that's what we need to prove. So suppose C star, suppose we have the two vectors U1, C star of U1 is C star of U2. Here I haven't bothered to put the P, but think of it always C star of P. And UI is tangent to gamma I. So in other words, it contains the curves I, where I equals 1 to 2. Then it means, well, what does it mean to say that these two what does it mean to say that these represent the tangent? Sorry. What does it mean to say that the two image vectors are the same? Well, we define C star of U1 as d by d lambda. Just look up above. It's got a little bit obscure. We just defined it as d by d lambda of C of gamma 1 of lambda. I got the right number. And then equals 0. That's equal to d by d lambda. The same thing, C of gamma 2 of lambda at lambda equals 0. But then, if this is what it means that this is what C1 is, and this is what C star of U1 is, and this is what C star of U2 is. So if C star of U1 equals C star of U2, then these two things are equal. But this is, by definition, the statement that this is the way we define tangency. Right? So this says that gamma 1 is tangent to gamma 2 at P. So therefore, of course, by definition, U1 equals U2. These belong to the same equivalence class. It's hard to see that it's even a proof because in some sense it's so trivial. But it certainly is true. So that's the second bit. The third bit is not quite as, it's also fairly straightforward, but it's not trivial to the same degree. You actually have to think a little bit, not just translate the definition. So what does it mean to say that the map is surjective? That means that we don't leave out any vectors. Right? So if that every vector in V comes from some vector U in the tangent space. So how do we, in this case, let's given a vector V, or in VC, we seek now some tangent vector whose image is this. So we need to find some curve whose tangent, after we transfer the curve over to V, using the chart map, its tangent should be V itself. So how can we do that? Well, that's not, if you think about it a little bit, it's not difficult. We just need to find in V itself a curve whose tangent vector is V little v. And then pull it back to the manifold via the chart graph. So what is such a curve? Well, there's the obvious curve, given a vector space here, and a vector in it, the obvious curve whose tangent is this vector, it would just be a straight line through that, parallel to that appropriately parameterized. Of course, you could find many, but that's the simplest one. So what is that curve? It says that gamma of lambda is equal to it says that we should, in the vector space, we should have lambda. We should map lambda to lambda times b. So back in the manifold, we pull that back. If we do that, then it follows that C. If we make this assumption, so let's consider this curve. It follows that then C gamma of lambda is equal to lambda times d. So d by d lambda of C of gamma of lambda is equal to d by d lambda of lambda b, which is just b, completely independent. For all lambda, this is true. So in particular, if I evaluate the mode at lambda, if I evaluate the left-hand side at lambda equals 0, then the tangent vector is b. And this was by definition I forgot to say, let us define U to be the equivalence class of gamma. In other words, choose a U, a vector U, an equivalence class to which gamma belongs. So U is the tangent vector. U is the tangent vector to gamma, and so by definition, then C star if we applied to U is equal to this, so that's equal to B. Okay, so we found some vector. We found some vector which maps onto V. So therefore, the map is also surjective. So it sets up a perfect correspondence between vectors in the tangent space and vectors in the vector space V. Recall that we also wrote this as a statement that U is equal to D gamma of lambda. That was our notation to say that gamma belongs to the equivalence class that defines U. Okay, so it's all almost trivial, but if you want to make sure that everything has been done correctly, then you need to go through those steps. Now that we've done that, now we know that this map, this push forward map to C star, is actually invertible, because it's a one-to-one correspondence between vectors in the tangent space and vectors in the vector space coming from the chart. So now we use it to define the sum of two vectors in the tangent space. So given that U1 and U2 belong to the tangent space of M at V, we define U1 plus U2 how? Well, first I'll leave up to P now, not worry about P. We take use C star to transfer the vectors U1 and U2 to the vector space V. Since it's a vector space, we know how to sum them. And then we transfer the result back using the fact that C star exists. I should have said hence C star is invertible, being a bijection. Okay. So that's the definition. What about scalar product? If we want to define, well, let me write this another way. It makes it, I think it's sufficiently clear, but sometimes it helps to write things a second way. So we will define that U is equal to U1, say U3. U3 is U1 plus U2, if and only if. This is just essentially putting the C star on the other side, if and only if C star of U1 plus C star of U2 is equal to C star of U2. That's another way of saying what the definition is. This directly defines U1 plus U2. This tells you when some vector is the sum of the other two. So that, if you think about it, these are the same, trivially the same statement. Now, what about scalar multiplication? Well, we can use the same trick. U2 is equal to lambda times U1 if and only if C star of U2 is equal to lambda times C star of U1. I've written this. I've written in the second form. So to multiply a vector by a scalar, you just transfer it to the chart vector space, multiplied by a scalar there, transfer the result there. Now, if you want to be, again, if you want to be careful, you have to show, so I'll leave it as an exercise, to show that this definition is good, that plus and times are, as it's called, well-defined. What does well-defined mean here?
Well, you're always
what?
You have to show it's the same for each chart.
That's right, because in setting up, just as before, in setting up this definition, I used a particular chart. What would have happened had I used another chart for this? You can prove that on the same lines that we proved well-defined in this, for the map C star itself, and in the way that we're just about to do now, to prove that the notion of tangency is well-defined. So, now we want to return to that question, the thing that we left hanging, which is the proof that the definition we made of tangency for two curves in the manifold actually is a good definition. So to do this, I think along the way, I'm going to introduce, as part of this, maybe one useful thing that can be done in parallel with this is to introduce this sort of modern, more abstract definition of derivative, which some of you will see, but maybe not all of you. Someone was saying last time after the class that it's actually called something that sounds very tasty, like gâteau derivative or something like that. I never heard it given that name, but I think I've heard it called crochet derivative or something. But anyway, it's the same. It's apparently another name for the same thing. But what it means is that, so this is now a small excursion, small detour to define a derivative as a linear operator. If you're not happy with this, then we'll say, in a second I'll say how it looks in coordinates, and you can just deal with the Jacobian matrix of partial derivatives. That'll be equally good. This idea of derivative as a linear operator comes up all the time, actually. So it's worth noting. In finite dimensions, it's not absolutely necessary, but when it comes to infinite dimensions, it's really hard to define derivative without this. Anyway, it gives, I think, a clearer sense of what the derivative really means. So let's consider vector spaces, which I'll call X and Y, Now here we had, this is going to be very similar to what we had before. We had maps going from the manifold to a vector space. But when we want to, that came from a chart. But if you have a second chart, you have a map from the manifold to a different vector space. If you want to compare what's happening with this one chart versus the other chart, then you're going to be mapping back and forth between those two vector spaces. And it's for that reason that we want to consider the notion of derivative for maps between two vector spaces. So that has to be some smooth map going from x to y. When we say as I said before, when we say that map is differentiable at some point x, what we're saying is it can be approximated in a sense by a linear map near x. So another way, what that's trying to say is that there's a map f prime of x, which we call the derivative of f at x. That's also a map from x to y, but it's a linear. It's not only a map, any old map. It's a linear map. So sometimes it's called a linear operator going from the vector space, and it's defined by the variation. If we say now, let's write this function y as using y equals f of x, as usual, then we say that infinitesimal variations of y are given in terms of infinitesimal variations of x by this equation. So this is not a linear equation. Now here I've used infinitesimals. If you don't like the infinitesimals, you can always do the same trick that we did in defining vector and replace these by curves. We could introduce a curve x equals, we think of x as being some curve gamma of lambda, of course now gamma is a curve in the vector space x, then this dy divides here by lambda, then we get dy by dx is equal to f prime of x acting on dx by dy. So that will define for you this f prime of x without needing to invoke the idea of infinitesimal. But the important thing is that it's this linear operator, f prime, that is the derivative, and it's telling you how to take infinitesimal displacements in x and infinitesimal displacements in y. Remember the picture we had. If this was x, here they're just one-dimensional, and this is some curve, and we're at some point x naught, say, and this is the curve gamma, that this infinitesimal displacement in x just corresponds to a small vector here. And what we're saying, again, is that as long as you remain close to x naught, the changes in y can be approximated by this linear function. This delta y can be approximated by a linear function of delta x. In fact, this is, if you want this definition of, so here I'll give the formal definition. This is this Frechet derivative, as it's called. We define delta y if I have two values, of x, say x1 and x2, and then y1 and y2 corresponding, y1 is f of x1 and y2 is f of x2, then I'm defining x2 minus x1 to be delta x, just the obvious and y2 minus y1 is equal to y, where y is always f of x, then for infinitesimal displacement, we said that dy was equal to f prime of x times dx. But for finite displacements, of course, it's not exactly true, but you want to demand that it be true to a very good approximation the closer you get to x naught. I guess I should have called this, in this picture, x is x naught. I mean, in this formula, when I write f prime of x, I mean that x to be that point where we're interested in evaluating the derivative, which I call x naught here. So what does this say? So it says that there's going to be a small correction, which we would normally think is of higher order, like order delta x squared. But the technical term is it's slightly weaker than that assumption, is what's called little o of delta x. That means that it vanishes faster than delta x vanishes. Now, I could make it all precise, but there's no need to, because we won't be whatever we'll be using things for, I think everything will be intuitively clear how the definition should go. And if you want, in order to make this, the reason I'm not making it precise is that you need to put some measure of size on the spectrum. And for that, you need to introduce what's called a norm in the vector space. That can be done in many ways. But the simplest way is to introduce a basis, represent the vector as a component, say a column vector of real numbers, just a set of components, and then use the sum of the squares as your norm, for example. And it turns out that the answer is independent of how you choose the basis. That is not that the norm is independent, but this criterion is independent. Okay, so this really is more or less, in practice, always means order of delta x squared. So in other words, the deviation from this relationship should be of a higher order than 1 in delta x. So is it really clear what this definition is? Sort of? Okay. Now let's just restate the definition in coordinates. So now I'll assume my vector space X is actually not just any old vector space, but it's actually R to the n, or just for fun, R to the m. And the vector space Y is equal to R to the n. So I'm allowing for the dimensions to be different. What does that mean? It means that a vector, remember the definitions of these things, a vector in the first vector space, little x, that means it's by definition just a set of real numbers, m of them, and a vector y in the second vector space is also equals, and vector y is also a set of real numbers, which I can call y1, 2y, n. And I say y equals f of x before. Remember, so now, what was the derivative? So what I want to do now is translate this sort of abstract-looking definition into something that'll be very familiar, which is the Jacobian matrix. So what we're saying is that dy, for each coordinate, dyi, if the map is differentiable, then we know that dyi is given by partial yi, partial x alpha. I use different indices here because their range is in general different. And dx alpha, right? Again, if you like, you could divide through by d lambda, so everything is finite. I won't do it. So this is true for any differentiable map where y equals f of x. So what it tells you is that f prime of x in this special case can be identified as the special case where the vector spaces are just Rm and Rm, the sets of real numbers. This derivative can be identified with dy, with the dy alpha, dx, dy I, sorry, dx alpha. So the notation should make sense. But if you think of it, if you just think of it, if you, instead of thinking of the vector as a string of real numbers, which is what we've done here, and therefore allowing us to define these partial derivatives, they're all just numbers. If you just think of the vector as what it really is, something geometrical, then you can write the relation in this way. And that way, it's just true in the vector, it's true given the structure of the vector space itself. It doesn't require you to choose a basis or coordinates in the vector space. But there's no, if you ever get in trouble with something like this, there's obviously no harm in going back to this. So, okay. Yeah.
So, the precise definition of that is what parameterizing things with curves, right? So the dy
Precise definition of which?
Of dy equals f prime of x acting on dx.
Well, the precise, if this was in the manifold, yes. But see, what I've done here, this is, I should have stressed more. This is only a definition for derivative of a map from one vector space to another. It's not as a vector. So in a vector space, we know what a vector is. We don't have to think of it as an equivalence class of curves. A vector is just an element of the vector space.
Well, the second definition of the curve, that tells me exactly what to do with it.
This one?
The one above it. Yeah,
yes. Oh, yes, you can, yes. Oh, that's true, yes. In order to give meaning to this statement, you can, that's true. If you interpret it like this, you don't need to have it, you don't need to see this. All you need to know is what's the meaning of dx d lambda. That's it.
And for that, you use coordinates, isn't that true?
Well, you don't, well, no, so there's the thing. If you like, you can, but you don't have to. You can go back to this definition. So this is a special case. You see, the curve is a special case of a map between two vector spaces. But it's just going, well, in this case, it was x, the vector space x. So it's a map between R, which is a vector space, and x, which is also a vector space. So I could, of course, in R, there's an easy measure of size, it's R itself. Here, to get a measure of size, you need to introduce, you need something auxiliary. I mean, there's no unique measure of size in this. There's a whole infinite family of them, which are called norms. But any one of them will give the same criterion for differentiability. But you could, of course, do it. But so the point of view I'm taking is that this is not to be defined. This thing object is not to be defined by introducing coordinates and then just reverting to this partial derivative. Or in this case, it would be total derivative, just with respect to lambda. It's just to be defined essentially by this feature that to first order, the change in y is proportional to the change in x. So in this case, we would have, so if we redo the same thing for this special case where x has become r and y has become x, then we would have delta x. So now we would have x is equal to gamma of lambda. We'd have delta x is equal to whatever you want to call the derivative, dx d lambda at 0, let's say, times delta lambda plus, I'll just make it order delta lambda squared for simplicity. But that's really what it's saying. It's saying that when you're near zero, assuming that x is gamma of 0, when you're near 0, then the map gamma looks like a straight line. So delta x is proportional to delta m. And if there's a deviation, it's order 1. So that's all, and that's what this picture is trying to say. So on the other hand, if it looks, if the map looked like that, it wouldn't be true because there's no good flat approximation to this. If this is x, then when you're near x, if you go up in one direction, it looks like this derivative. If you go up in the other direction, it looks like that derivative. So there's no single linear map that gives a good approximation. And of course, I go back to more pathological ones. This is the simplest case. Any other questions? So now that we've set all this up, let's go and prove that tangency is well defined. Was well defined. So remember the picture that we. So again, it's a set of equations, all of which, in some sense, look obviously true. That's what makes it hard. So, you think of how exactly you're supposed to prove it. Let's recall the picture. And so we have now two curves, which I call gamma and gamma bar, and we want to know that we correctly define gamma and gamma bar being tangent. So we have again the two chart. In order to define it, we use the chart, and now we want to consider a second chart. Actually, we have. I almost have the picture already. I can redraw the picture. So we wanted to define a second chart and check that if gamma and gamma bar are tangent in the first chart, then they're tangent in the second chart, and vice versa. This should be V eta. And so what do? So we have to look at the transition maps between the two. So let's call that transition map F. I didn't have enough room. So F, that's what I called before. If you go back to when we introduced charts, F of C eta. It's the transition map, the glue that glues a little bit of the vector space eta into the vector space C. So that's the setup. Now I want to define, put this symbol for commute. That's telling you that this diagram commutes, as people say, meaning if you go from here via eta and then you go via F, you get the same result as if you go directly via C. In other words, C, put it over here. C is equal to F, circle eta. So that implies, now let's look at the two curves. That implies that C of gamma of lambda is equal to F plus eta of gamma bar of lambda. I'll give this a name, B, and I'll give this a name, this eta of gamma, W. Now, using the definition, we've assumed that F, remember, the definition of a smooth manifold was that these transition maps are differentiable. So that means we can apply the definition of differentiability, and that says dV is F prime and W dW. Here, of course, V is equal to F of W. The definition. Therefore, I can divide through by d lambda. dV d lambda equals F prime of W dW d lambda. Now take lambda equals 0. and plug in what the definitions were, and we get the dc of gamma of lambda divided by d lambda, and lambda equals 0 is equal to f prime of w naught, I've called it here, d eta of gamma bar. I wrote gamma here, but there's a gamma bar of lambda. That's there, where W naught is just what I call eta p. So we have, these are as usual in that picture, these are all vectors at p. And the same thing, and so, oh no, sorry. I did mean W, I did mean gamma. So I'm just looking, someone should have called me out on this. What I wrote is really wrong. So this is just saying, C is just F circle eta. So now I apply both sides to the same curve, gamma, and I get this set of, I get this equality. So this equation holds. Okay. And the same equation holds for gamma bar. So I replace gamma by gamma bar. But now, let's assume we want to assume that gamma and gamma bar are tangent with respect to the chart eta. Right? So if we judge tendency in the chart eta, then we say that they're tangent. Well, now we just apply what that means. That just by the way we define it, that just d eta of gamma of lambda d lambda is equal to d eta of gamma bar of lambda d lambda at lambda equals 0. That's just a statement that gamma and gamma bar are tangent. Now just apply f prime of w to both sides. F prime w naught to both sides. But here again, f prime and w naught. But now we look at that equation by applying f prime of w naught to d eta blah blah blah, we get the same thing with c. So that says dc of gamma of lambda equals blah blah blah. Dc of gamma bar of lambda. This is equal to that, and this is equal to that. So therefore, these are also equal. But that says, that's just the definition of gamma and gamma bar being tangent with respect to the chart C. I guess I use this notation with respect to the chart C. Gamma bar with respect to eta, we can write it like this, and this is with respect to C. Okay, so that's the proof. So we proved that if they're tangent with respect to C, to eta, then they're tangent with respect to C. Conversely, if they're tangent with respect to C, well, we just reverse the roles of C and eta, and we get a proof of the tangent with respect to eta. So the notation is a little, so maybe the notation is a little clumsy or a little hard to follow at first, but the idea is very simple. we just have, so let me just restate the idea. So we have these two curves. We have, say, one of them is gamma into M, and then, well, I have the picture up there already. I don't need to redraw the picture. So if you imagine looking at that picture starting from R and going to big C and going to d eta, you have this picture. You have the map C circle gamma, and you have the other map eta circle gamma, that's in d eta. And then you have the map F, that I called F, C eta, that takes you from the one chart to the other, that glues them together. We have this is a commuting diagram. All we've done now is apply the notion of derivative to all of this. So we've just replaced this, we've said we can just put primes on everything. This is basically the chain rule. If you were to write it out in coordinates, you would recognize it as a chain rule. And if you were to write it out in this more abstract way, again, you would recognize it as a chain rule. So, I mean, there's nothing more that I have to prove here, because I proved everything, but just to get the intuition of what's going on. You have this diagram that commutes, and of maps, the differentiable maps, and if you pass to the derivatives, the derivatives are just linear approximations to the maps. And so if the original maps compose consistently, then the derivatives also compose consistently. And that's all that there was to it. Okay, any more questions then? Yeah.
Could I ask another question about the abstract definition?
Yeah.
So if I wanted to concretely compute stuff with that definition, so then I'll have to put a norm on X and a norm on Y.
Right.
Then I'll know what it means to compute the norm of delta X, for example. I can pick two vectors, pick their difference, and take the norm.
Right.
And then with that definition, then I can compute F if I'm patient enough.
I mean, you can compute.
I can compute the derivative at point X.
You can, you can search around. If it's differentiable, you can find the linear operator that does it.
So then, is this statement that then if I would change my norms in both vector spaces, then the number, then I'll get the same number? Is that the same?
You'll get the same F prime of X. You'll get the same F. That's the statement. Because, how can one see that? It's because this map is defined by, let's even put an order delta X. I didn't even define what this little o is, so let me just say big O order delta X squared, so everyone has a sense of what that is. So that's a slightly stronger requirement than you need, but it's the typical case. So the statement is that, what does it mean to say it's order delta X squared? It means that its norm will vanish quadratically relative to the size of the norm of this. So all you need is that one norm vanishes quadratically if and only if the other one vanishes quadratically and vanishes linearly if and only the other one. And that, it turns out that that's true, so it turns out that any two norms are bounded by each other, by some multiple of each other. So so this is a side, this is just by way of answering your question. Suppose you have two norms, let's give them a name. So usually they're written like this, but let me just call it N of V, the norm of V. Then suppose I had another one, N prime of V. What you can prove is that there always exists some constant greater than 0, such that for all V, for all vectors, the first norm is bounded by this second norm. It's not necessarily that N of V is less than N prime of V, but it's less than some multiple of N prime of V. And that's true for any two norms. That's what you can prove. And so if it vanishes, but what order it vanishes as doesn't depend on an overall scaling. So if it vanishes at second order in the one norm, it will vanish at second order in the other. So this you need to prove. This relies crucially on being in finite dimensions. If you want to define a derivative in infinite dimensions, then you need to specify, you can't just get rid of the norm. You need to say its derivative with respect to it satisfies its equation with respect to some particular dimension. So like if you're doing in Hilbert space, you'd have this L2 norm probably. But if you change the norm, you change the definition of derivative.
I have a question.
Yeah.
I don't see how that's the chain rule in that community diagram.
Oh, okay. Well,
The chain rule is a product, and it's not just a pure composition.
well, it's a lot like it. Suppose you have suppose you have a map from sort of x, y to z, and we want something like partial z, partial x, partial z, partial y, and partial y, partial x. But what does it mean when I've multiplied these together? It's really a composition. If you write the southern partial derivative, as you might be used to seeing, this is a composition of two matrices.
So it's the fact that these are linear maps that.
It's yes.
Okay.
Yeah.
Sorry, I'm not sure how that statement you just made about the norms bounded by a constant follows. If we consider the two norms,
You're not sure why this is true, or you're just sure?
I'm not sure why that statement NB is less than Cn prime B is true. I mean, if you consider,
I haven't proved. Yeah, I just asserted it.
I mean, I can think of a counterexample.
Oh, okay, that's good. Let's have it.
Absolute value and absolute value squared on the space R.
So absolute value squared is not a norm. Yes, I haven't. I didn't actually give you the definition of a norm. Part of the definition of a norm is that it scales linearly.
Oh,
so the
okay.
norm of lambda times v. So that's a good point. Not any measure of size is a norm. A norm is something very special. But it implies that if it's a norm, then the norm of lambda times a scalar times a vector is the absolute value of the scalar times the value of the vector. Other questions? Okay. So I want to. So, as I said, the other thing here, I didn't check something. I forgot what it was, but you could check it in the same. Oh yeah, but the addition and scalar multiplication are well defined. Here's also an interesting thing, which I forgot to write down. I chose not to write down at the time. That here's just for your own amusement, if you like, to prove that the following is another definition of scalar multiplication. So prime definition. If B, so B is gamma dot of 0. In other words, gamma is we're back to the manifold then. So V is the vector, I guess you call it U. So here was my manifold. Here's the point P. Here is my curve gamma. Here's the tangent vector U. You might think of another way to multiply it by a scalar. If I want to make it twice as big, all I have to do is traverse this curve twice as fast, reparameterize the curve. So you might want to, for your own amusement, convince yourself that that's equivalent to the definition that I just gave there. That if B is, that if I want to multiply D, which I've now changed to U, by lambda, then that's the tangent vector to some other curve, gamma prime, where gamma prime is gamma prime of lambda. Oh, there's too many lambdas. Gamma prime of mu is equal to lambda, is equal to gamma of lambda times mu. Mu is the parameter, right? Since I've already used U for this there. So I just traverse it down. So you might want to prove that those two definitions are equivalent. Then finally, I wanted to mention another way to define a vector, which you'll often see, and then talk about the components of a vector. So another way to define a vector, which you'll often see in differential geometry books. I'm not actually sure in our textbook one of them might use this definition. I'll just state it. We won't be using it. But I want to state it because, as I said, you often see it, and you often even see a notation that's inspired by it. And it's kind of slick. So I have to define what's called derivation, which I'll do for you sort of in a second. Maybe I won't. So the statement is that a derivation on this space C infinity MR. What is this? This is the space of smooth functions from M to R. Is a vector field. Vector field. Of course, when I say vector field, I don't think we actually formally defined it. But it just means, of course, a field of vectors. So it means attaching to every point of the manifold a vector in the tangent space that belongs to that point. But this is, except for the fact that I haven't defined derivation, this looks like a very quick, simple definition of a vector. And it is, actually. So it makes it easier to define things like U1 plus U2. Because now we just have to add the derivation, and that's trivial. But, so I would say this definition is slicker, but now I need some help from someone, maybe you. It's less, this word, but I don't know how to translate it. Anschaulich.
Anschaulich.
Anschaulich, yes. Yeah, I know, I can.
There's an A in the middle.
Oh, did I leave something? Yeah, anschaulich. But what's the English equivalent of this word?
Maybe intuitive?
Okay, sort of. Yeah.
I can visualize it.
Visualize it. Okay, so it's some combination between being intuitive and being visualizable. So it's easy. It's hard to. It's slick, but it doesn't show you what's going on. Whereas here, using the equivalence principle as the basic idea, you do see what's going on. But if you just want something to streamline some of the proofs, you might use it.
Concrete?
I haven't. What?
Sorry, I was just thinking of another word. Concrete or
yeah, maybe
abstract.
Well, I don't know if it's more concrete, because in a certain sense it's a bit abstract.
No, I mean as a translation for anschaulich.
I know you're suggesting it, but I'm just wondering if it's an appropriate word to use. But anyway, it's yeah. So it's less anschaulich. The trade-off between that often happens in that way. To really understand what's going on, you want to do something in a slightly clumsier way. But to make it beautiful, you want to do it in a slicker, more elegant. To make the machinery is more oil. I won't define derivation unless someone forces me to. But what it basically means, its essence is that the Leibniz rule of neutral derivatives of products. So now, okay, so the one last thing that I want to do before leaving, we're almost finished with the notion of vector, and then we can talk about the metric field. But the one last thing I want to do is define the components of a vector. So you might think that this was a strange order to do things. We've gone through defined vectors, how to add them, everything. We never mentioned components of the vector, whereas you might think that that would come first. Why did I do that? Not just to try to be obscure, because I'm hoping that way it helps you to think about vectors as geometrical objects, which is what they really are. So vectors, as far as general relativity is concerned, are just what they are in sort of undergraduate physics. A vector is like an arrow or something like that. You don't think of a vector as a set of three numbers when you first learn about it. And by the same token, you shouldn't really think of a vector in space-time as a set of numbers, and you shouldn't think of tensors as matrices of numbers or higher dimensional arrays of numbers. It's important to feel at home with theory to get this geometrical sense. This geometric reality, kind of what I'm thinking about it. So that was sort of, it wasn't by malice that I put the definition of components last. It's with that in mind. But now we do, obviously you would be at a disadvantage if you didn't even know how to attach components to the vector. So how do we do it? Well, at this point it's trivial because we've already defined a way, when we say components, of course, we always mean components with respect to a chart, and more specifically, a coordinate chart. Which means, of course, a chart whose codomain is actually a vector space. So that was what I called B sub C. Now we just take it to be R4, assuming we're doing the space-time case. So with respect to that, we want to turn the vector into 4 numbers. We want to turn the vector into 4 numbers. And how do we do that? Well, we already have defined this map. Just push forward this linear operator, C star. That'll turn the vector into a vector in this V sub C. But if this vector space has a distinguished basis, some God-given basis, then we can just express that vector in terms of that basis, and it becomes 4 components. And of course, R4 does have a God-given basis. It's just the basis. It's just the basis, whose elements are 1, 0, 0, 0, 0, 1, 0, 0, so on, 0, 0, 0, 1. So the point of R4 is a set of 4 numbers by definition. So it has this natural basis, which tells us, just going in circles, that yes, it's really a set of 4 numbers. So here's the definition. So that's the idea, and here's the definition. That I'll do a little more carefully. See, mapping its domain into R4, the coordinate chart, and let B be a vector in the tangent space M at P, and that then the components of B with respect to the chart C are, that's what I said before, the components of the vector C star of B acting on B in alpha. That's the definition of components of the vector. However, it's very useful to think also in the following way, that I'll leave for you to convince yourself. So here we've said this, that if we think of an arbitrary point P of M, of the space-time, so think of that, then C of P, but I don't mean just, so let this be any point. I don't just mean the point at which I'm trying to find a tangent vector, but just take a generic point in M. Then C of P consists of four numbers, right? x0, x1, x2, and x3. What does that mean? That means if I take any point in M, I get from it four numbers. If I just focus on the first one, then that's a scalar field. Right? It's just attaching to every point of the manifold a number. And here's a second scalar field. So therefore we have four scalar fields, which I'll call x0, x1, x2, and x3. Okay. In other words, x mu, what I call little x mu, the mu coordinate of the point P is just equal to x, this capital function of the point P. Okay. I said everyone is happy with the term scalar field, which we didn't strictly speaking define. It's just a map from the manifold into the real numbers. It's a real scalar field. Then, so here's the claim, which I lead you to convince yourself, that B mu, mu's coordinate of B, I think I switched, I was calling it U before, but now I'm calling it B, tangent vector, U equals 0, 2, 3. It's the directional derivative of x mu with along the curve gamma that defines v. So, in other words, d mu is equal to d by d lambda of x mu of gamma of lambda if we wrote it like this, if gamma belongs to the equivalence class that defines v. So the mu's component, this is what you're used to, right? It means that the mu's component of the vector is just the gradient. If the vector is a tangent vector to the curve gamma, then its mu's component is just the gradient of the mu's coordinate along the curve gamma. Okay. So this is just this formula. If I didn't write it in such a careful way, I would just say v mu is equal to dx mu d lambda, which is probably a form of the definition that you've seen often. So much for vectors. Now, mind you where we were. We'll just make a start on the metric field. So far, we've been just going through the structures that Minkowski space has and seeing how they generalize to curved space time. We had topology. That gave us a notion of topological manifold. We had the linear structure of Minkowski space, that's given us the notion of vector. Now, of course, Minkowski space has a metric, which we usually represent either by A and mu, or by the associated line element, ds squared, as it's called. This is the other two, from the point of view of relative, and then we have the causal structure, which will come to in a bit. So those four structures, the first two are what I call the four background structures. They're just fixed once and for all. They don't participate in any equations of motion. They're not influenced by whatever matter but might be present or gravitational waves. The next two are dynamical structures. And of course, the metric, when it becomes dynamical, is called the gravitational field. Although I gave a little sermon the first or second day saying that what we call gravity in the naive sense is not just defined by the metric, it's defined in part by the metric, in part by our acceleration of our coordinate, of our reference frame with respect to the rest frame that's natural for the metric. But anyway, this is usually called gravitational field. So what we want is to define what is a Lorentzian metric on a manifold. So if you want to read about this, well, section 2.2 is just section 2.1, I hope, 2.3 and 2.5. More or less covers the same material. Now, as I said, in Minkowski space, there's two ways of thinking of the metric. You can think of it as this tensor, although we haven't defined tensor, so you may think of it as if you're not used to that, you may think of it as just a matrix. But anyway, it's some sort of geometrical object at the end of the day. Or you can just think of it as that thing which allows you to assign lengths to curves. In particular, it allows you to assign a proper length. And if the curve is time-like, that really represents physically proper time. So if we define metric in the best way, again, the most intrinsic, most geometrical way, we will have to define, because this is a tensor, we'll have to define what is a tensor in curved space, and then the metric field will be a tensor field in curved space. However, I don't want to put, that would be a whole bunch of more just mathematical preparation. I don't want to postpone the physics that long. So I'm going to define the metric, first of all, in the sense of, I'm going to define it in the sense of the line element, and to do that I'm going to do it with respect to a chart. Right? So for the moment we'll consider, in fact, a coordinate chart, not just any chart. So basically we imagine a little region of the manifold which has a coordinate system on it. And with respect to that, we are going to define the line element. Actually, I could get by, instead of assuming that the coordinate chart, instead of assuming that they're actually coordinates, it would suffice to assume that the vector space of the chart was in some sense naturally identified with Minkowski space. All I really need is to take the metric information. It's again the equivalence principle, if you like. Locally, the manifold, the space-time is like M4, and then we're just importing the metric information from M4 back into the manifold. But for simplicity, let me assume that it's a coordinate chart, so it's not only M4, but actually it's M4 with Cartesian coordinates, x, x0 to x3. Now, actually, why have I written this? I'm not sure, but what would have been more sensible is to use, I want to reserve the x's for arbitrary coordinates of any coordinate chart. But for Minkowski space, I want to use coordinates y0 to y3. So that's in Minkowski space. I'm going to assume that the chart is such as to define an inertial frame, so that means that locally y0 to y3, that the first order, the metric is given in the manifold by the same formula as it's given in the Minkowski space, which is of course that ds squared is equal to minus dy0 squared plus dy1 squared plus dy2 squared plus dy3 So I'll assume that at some point P naught in M, there exists a coordinate chart y with coordinates y such that this equation holds. This is, and this, of course, we all write, as usual, we write this as eta mu nu dy mu dy mu. Where eta mu nu is now really, it's now really a matrix. So it's minus 1, 0, minus 1, 0, 1, 1, 1, 0. However, this, okay, so we can assume that this equation is true at P naught, but if we go a little bit away from P naught, then as usual there'll be higher order terms. And we cannot assume that in some finite neighborhood of P naught, this formula holds, because that would say that the spacetime is flat in the finite neighborhood of P naught, which in general it's not. So the basic assumption is that, if you like, of the equivalence principle is, so the equivalence principle says that such a chart always exists. So that'll be our assumption. So assume that at every point in the manifold we can find a coordinate chart such that the line element, which of course we're assuming there is something that's determining length in the manifold, and such that something can be expressed in this way at P naught, for instance, just displacements about P naught. So what does that tell us? However, we don't want, that would require you for every point to use a different chart. That's obviously hopeless. So let's translate this into a statement that will be true in a single chart. What is this telling us if we now pick a single chart to cover not only that point P naught, but a whole region around P naught? Well, so now we just need to translate this. We need to translate this formula into an arbitrary coordinate system. And we'll quit. So let the x mu's be some coordinates belonging to some other chart. Let's just re-express this equation in terms of the x's. So it said, it said that ds squared was equal to eta mu nu dy mu dy nu. But since change of coordinates is always a differentiable transformation, we can rewrite dy mu is dy partial y mu partial x alpha times dx alpha, and dy nu is partial y nu partial x beta times dx beta. So in this arbitrary chart x now, it takes the expression for ds squared, takes this form, ft, and this we give a name. We call this the metric components, actually in this case, of the metric tensor at x. It's actually at the point p, but in the coordinate system, the coordinates of p are x. So what we learned is that in an arbitrary coordinate system, at the point p, we can write ds squared as g alpha beta dx alpha dx beta, where g alpha beta is given by this expression. But now there was nothing. I mean, I could have done this at any point. No matter at any point in the manifold, I could make the same argument that I would learn that the line element must take this form at that point in the manifold. Therefore, we can say that in general, the line element throughout the whole domain of any coordinate chart must take this form, where this is just some matrix. We haven't yet said what matrices are acceptable. All we've said is it must be some matrix such that I could find some other coordinate chart in which the metric took this simple form of eta mu nu dy mu dy. So these are just 16 functions, really 10, given symmetry. So these 16 functions define G alpha beta, and conversely, any set of 16 functions is a candidate for the metric field at that point. However, is it a valid candidate or not? So I have to make some limitation on what set of 4x4 matrix I can actually represent the metric field. First of all, of course, it has to be symmetric. That's trivial. It cuts it down to 10. But there's also some inequalities that it has to satisfy. We can see that in the following way. So not every G alpha beta is okay. Because, for example, let's go back to where it came from. Had we started, if I can find where did it come from? It came from here. Notice I put 1 minus sign and 3 plus signs. That's because I'm using that convention, but most importantly because we know that one of them has to have the opposite sign to the other 3. I could have gone through the same exact derivation that we just did with the plus sign there, and that would give me another metric. But that metric wouldn't obey the equivalence principle. In the neighborhood at no point would it look like Minkowski space. It would look like Euclidean space, not Minkowski space. So we need the so there's an implicit condition here, which is what's called the signature of this matrix G alpha beta must be that Lorentzian signature minus plus plus. Then we have light cones and so on, everything that we associate with space-time. So with that proviso, this is the most general, kinematically speaking, we haven't put field equations yet, but kinematically speaking, this is the most general kind of metric that you consider in relativity. So at this point, in space-time, we haven't worried about subtlety, global subtleties like closed time, like curves and so on. But as far as the local structure, we define the gravitational field by giving a bunch of charts, and in each chart giving these 4 functions. Shortly we'll see that this can be thought of as a tensor, but to do that, we have to do a little more preparation. So that's the main thing. The other thing, which I didn't quite get to do, not that one page more. The other thing I wanted to define along, which we'll start next time, we defined a line element. We defined a line element, and using that we'll be able to talk about the length, proper distance along a curve, which physically will mean, if it's a time-like curve, elapsed time, proper time measured by a clock following that trajectory. The other thing that's important that you need almost everywhere is the volume element. So we not only want to be able to define length along curves in the manifold, we want to be able to define volume, of regions in the manifold, smaller regions, and using that we can define integrals, and we'll need that for defining gravitational action. So along with the line element, we also need the volume element, which I'll give a name now, dV, but we'll derive what it is next time, using exactly the same strategy, going from the equivalence principle. Most of you will know what it is, so I'll just remind you. It's just the square root of minus 3 d4x, but we'll see why that's the right one in the next one.